Okay, well, hello everybody, and welcome to this next in our series of Kickstarter Colloquiums. These are a platform for all of the various projects that have been done over the last year for the TVS, Stars, Milky Way, and the Solar System Science Collaborations, and hopefully are projects that prove of wider interest to the whole community. So we're having a series of talks of a number of different projects, and after each of the talks, we'll have time for questions. So feel free to post your questions in the chat screen throughout the talk. As you've just heard, the colloquia are going to be recorded, and the recordings will be posted on YouTube after the event. So if you prefer not to appear on camera, please switch your camera off. And in the interest of hearing the speaker during the talk, please mute your microphone if you're not the one actually speaking. And so with that, I would my pleasure today to introduce our speaker, who is Christian Aganze from the UC San Diego. And he specializes in the study of low mass or ultra low mass brown dwarfs. And he's conducted an investigation into what we will discover about this population with the LSST data. So, Christian, please take it away.
Thank you, Rachel. Let me share my screen. Can you see my screen? Okay.
Yes,
Great.
we can.
Yeah. Thank you. Thank you for having me here. As Rachel said, my name is Christian Aganze. I am this is my last year in grad school. I'm at UC San Diego, and I work on low mass stars and brown dwarfs. And my talk is going to be about brown dwarfs and low mass stars with the HST surveys that we did, and then with the Vera Rubin Observatory. I figured that I had 45 minutes, so I'm going to also talk about my HST survey work. This is in collaboration with people at UCSD, but also John Gies is at Delaware, and so I'm excited about this. So the picture here is something I downloaded from the Rubin website. It looks like it was taken in May. Looks like construction work is going on. So just a little bit of an outline for my talk. I'm going to talk about brown dwarfs and how they fit into the context of galactic archaeology. So if you keep seeing the word UCDs or UCD, just mean it's a word to say just low mass stars and brown dwarfs. And then I'm going to talk about my work with HST surveys, and then I'm going to talk about our Kickstarter grant, which was on simulating Ultracool Dwarfs in the Rubin observatories. So just to orient you, these are some of the guiding science questions that we're investigating in this work. We're trying to understand how brown dwarf and low mass stars fit into the picture of the Milky Way structure and evolution, meaning do we have the same number of Ultracool dwarf in the disk? So the fraction of disk to halo stars, is it the same for Ultracool dwarf versus main sequence stars? How does kinematic heating work in the disk? Do we have the same effects, even low mass stars? And we want to really understand the effects of metallicity on the hydrogen burning limits and the hydrogen burning minimum mass, so that this can actually inform us about models of brown dwarf evolution. So just a bit of an introduction. Ultracool dwarfs is a fancy term to say brown dwarf and low mass stars. They essentially objects that are below 0.1 solar mass. So here I'm showing some cartoon version of this. So you have like the sun on the left side, and then M dwarfs, which are around 3,500 Kelvin and below in effective temperature. And then we're showing Jupiter here. Jupiter is not Ultracool dwarf. It's just these objects typically have the same radius as Jupiter within an order of magnitude. So you can also think of them as the bottom end of the IMF. So if you count how many of them there are in the local neighborhood, you find that more than 20% of them, of the stars in the local neighborhood, are Ultracool dwarf. Ultracool dwarf have interesting evolution properties. So in this image, I'm showing the evolutionary model grid from Burroughs et al. 2001, where they show effective temperature on the y-axis and logarithmic age in billion years on the x-axis. So stars will be the object that, and this is colored by mass. So stars will contract into the main sequence and then probably fuse deuterium or stay the same temperature. And then brown dwarfs will cool down with time because they don't have enough fuel in their interior to to keep the same energy. And then planets here as a label just to say that once you start getting into this low temperature object, their spectra and their evolution looks almost like what you have with planets. If you look at the spectra of this object, they peak in the infrared. So mostly this an image from the Burgazar et al. Review paper. So on the y-axis, we're showing the flux, scaled to some arbitrary unit. And then on the x-axis, we're showing the wavelength. They tend to pick a 1 micron. And then they also have very interesting chemistry in the atmosphere, dominated by water and methane, CO absorption features. And these are really interesting chemical information, which mostly because this object don't are fully convective and don't fuse hydrogen, we can actually probe the original abundances from their progenitor molecular clouds. If you look in the local neighborhoods, they're extremely common. So here's an example of a distribution of object within 10 parsecs. So on x-axis, we're showing spectral type versus number of stars that you see. It turns out that if you look at ultracool dwarfs, they tend to constitute a large fraction of 10 parsec sample at least. And people have been trying to actually do this type of star counting for a while. So for instance, in the ultracool dwarf regime, people have measured the luminosity function using surveys like 2-mass WISE. So next axis here, I'm showing the effective temperature of the object versus space density in beams of 150 Kelvin. And this is just looking at the volume limited survey within 20 parsec. So each one of these dots is a measurement, so how many objects there are within this volume bin. And then each one of this line is an evolutionary model that also include the IMF and the volume that we're looking at. It turns out that this object tend to fit to a power law IMF, and then there are differences between evolutionary models, and then there are differences on, so these different colors here represent like the smallest object that can form. So if you expect that the smallest object that can form is 10 Jupiter masses, you get this one bright line, versus if you assume it's 1 Jupiter mass, you get a different answer. So most of these depend on the lowest temperature bins, and a lot of effort have been trying to characterize, basically get a volume complete sample within the low temperature regime. And these are probably too faint to be detected, to be fully surveyed with LSST, but most of this work is being done by people looking at WISE. So these discoveries of ultracool dwarfs have mostly been local, meaning that we're stuck within the 100 parsec sample, and which is a minuscule volume compared to the size of the actual galaxy. So here I'm showing an image of the galaxy. It's a cartoon version that I stole from Adrian Price Williams' talk from the AAS. And then, so we tend to live in this thin disk area dominated by metal-rich stars, probably younger than thick disk stars, which are more eccentric and older. And then you have, outside of this, there's still a halo, and we are inside this dark matter halo, but dark halo. So we are around 8 kpc from the center. So that 100 parsec volume does not really probe different galactic environments. So my work is really trying to put ultracool dwarf in the galactic context, trying to understand how does the evolution of brown dwarf tell us something about the Milky Way, and vice versa. Can we use something about the Milky Way that was constrained from higher mass stars to say something about brown dwarf evolution? Looking at the Milky Way with further resolution, so this is some example of one of the biggest ideas that came out of Gaia, was that the Milky Way halo and disk were formed from these merger events. So for instance, Gaia Enceladus. So in this case, I'm showing the velocity distribution of stars from the Gaia. And this is computed from this is taken from the Helmy review paper, but the paper was originally from Koppelman 2018. So on what we see is that the thin disk is dominated by these progress stars that are mostly moving slower. So they have a much slower velocity dispersion, not moving slow, but have a slower velocity dispersion. compared to a kinematically heated hot disk that was mostly formed from, again, the merger Gaia Enceladus. And then we have this halo star, which is mostly retrograde. And halo stars are mostly, again, the large fraction of them are from this Gaia Enceladus merger. And then we can also see the same effect in metallicity. So we've plotted on this axis, x-axis we're showing the the metallicity versus alpha abundance. Most of the thin disk stars are low alpha, and then thick disk star would be high alpha population, but still slightly metal rich than halo stars, which tend to be metal poor and low and high alpha. And this is again fitting to the merger hypothesis. And high alpha stars in the disk in the halo tend to have high eccentric orbit. So they're moving on more extreme eccentric orbit compared to object in a thin disk. This entire picture does not include brown dwarfs because Gaia was not sensitive to a large fraction of these objects. But we've been able to see some halo dwarf in the Milky Way. So for instance, this is in the local neighborhood. For instance, this is ACSS 1256-0224. It's like a minus 1.8 metallicity object that's moving. So in this, I'm showing the orbit that was computed from the Logier et al. Paper. So next axis is showing R versus Z, and this object goes to up 10 kpc in height. So this is a great halo candidate. And then if you look at, there's some interesting objects in this. So if you look at the distribution of this object within a 20 parsec sample, so this is a compilation from the Su et al. 2021 paper, which is a tumor diagram showing the different populations. So the yellow will be L dwarf, and then white or blue, I guess in this case it's blue. These are M dwarfs. It turns out that the local L dwarf population is highly dispersed compared to what we expect. Again, because L dwarf is a young phase of brown dwarf evolution, we expect this population to be younger. But if you look at their kinematic dispersion, they tend to be highly dispersed, even within 20 parsec. And this is a hint. One of the resolution to this problem was that L dwarfs have in the local neighborhood have a significant fraction of thick disk population. So just looking at these interesting orbits and kinematics and metallicity, we can start understanding this metal poor population. But again, we're still limited within the 20 parsec. So I'm going to talk a little bit about my work on trying to find objects that are at kiloparsec away using HST surveys. And then I'm going to close with what we expect to see with the Vera Rubin Observatory as we supported by Kickstarter grant. So in the HST surveys that we did, so this is just to motivate you. The idea is trying to find brown dwarf at kpc or above 1 kpc to kind of start understanding brown dwarf in the Milky Way context. So people did this a long time ago. So for instance, this is a paper where they tried to identify brown dwarf at large distances using HST SES fields. And they found 28 LNT dwarf, mostly selected by their colors. So in this case, they're showing, I think, Z versus, I minus Z. And this is really a great way to do it. But the problem is that brown dwarfs were not confirmed because you're only looking at one color and they could be just anything. So an alternative to that is to use GRISM surveys. For instance, this is a paper from Masters 2012.
Christian, sorry to interrupt, but we do not see your slides any longer. Can you please reshare them?
Sorry, let me share that again. I apologize. Can you see my
That's
slide?
better. Yes, we can see them. Thank you.
Yeah, sorry. So there's some surveys that were using GRISMs. For instance, this is a Masters of 2012 where they're looking at WISPS 3 surveys. Each one of these little images is a 2D spectrum, and then the 1D spectrum is shown. So they found 3 T dwarfs, and then they're showing also the fit to a template. So they found T3 dwarfs, but our goal in this paper was trying to expand further to larger distances by also including a larger sample. So we looked at the two surveys, so WISP and 3D HST. And the way these surveys work, they were looking at high redshift galaxies, and they get contaminated with brown dwarf in the foreground. So in this case, I'm showing like a cartoon image of HST and the pointings of these surveys. They're mostly looking away from the galactic plane, and they're looking at random pointings, which is great for us because we can start probing different galactic populations. So this is what the data will look like. So you have an image on the left side, and then the GRISM image will be on the right hand side. So this will be like an image at 1.4 micron versus 1.6 micron versus a spectrum at 1.4 micron. So the idea was to go into this data and select brown dwarfs. To do that, we use a template, a set of templates. So these templates are from the Specs Prism library that's maintained by Adam Burgasser and collaborators. And I'm just showing some typical templates. So an M7, L0, L5, T0, T5. Again, these are spectra. So on x-axis is the wavelength, and the y-axis is the flux. So we chose different regions that are sensitive to water and methane. And if you plot this, basically the ratio of fluxes between different regions, we call this a spectral index, you can identify brown dwarfs. So if you plot this in a random set of objects, they'll mostly be random because, again, this object probably don't have a lot of methane and water because they're mostly galaxies. But if you plot brown dwarfs here, they will fit into a pattern depending on the strength of water and methane in the atmosphere. So then you can just select them. And then, so we're able to identify some objects here, which I'm showing in blue. And then you can say, how are some of these objects outside of this box that you defined? So we use an alternative method. So you can see that there are some disadvantages to doing this, such that you can actually get contaminated with a lot of foreground points because these boxes are arbitrary in the sense that the limits of the box are not really that constrained. It's just a rectangle. So an alternative method is just using machine learning. So just a quick review of what machine learning does. In this case, I'm showing the method that we're using. It's called the supervised learning method, where we feed it. The typical problem is you have a bunch of images. One image is images of cats versus image of dogs. And if you feed this into supervised learning machine, and then you give this supervised learning machine new sets of images, it will be able to label them. So we've been able to train students to use this method. You can go check out their research notes on the RNS website. So we've been able to train them to first do some classification versus brown dwarf versus non-brown dwarf. So that's the first plot that I'm showing here, using a set of colors in different surveys. And then we've also been able to train them to classify subtypes of brown dwarf. So in this case, I'm showing an image from the second research note where they predict the label or the spectral type of a brown dwarf based on its colors. But for my project, I was using this method to just identify brown dwarfs in this large survey. So our training set was of 3,000 known ultracool dwarfs from the Specs Prism library. And then we had 150,000 object flags as galaxies. And then we were predicting on 100,000 objects known as point sources in these surveys. We measured, again, the spectral indices, signal-to-noise ratios, and other statistics. And we grouped things into galaxies, brown dwarfs that are late M dwarfs, so early M dwarfs, late M dwarfs, and then L and T dwarfs. So what we found is that, so what I'm showing here is the result of this classification. I'm showing different methods and then how many objects they predict. And then the last column here is the number of contaminants, meaning the number of objects that we have to confirm by eye that they are not brown dwarfs. The idea here is that most of these methods predict the same number of objects, which is good. But the machine learning method are particularly good at reducing the number of contaminants. So for instance, the index method identified 3,400 contaminants, but the machine learning methods were only identifying 100 contaminants. So an order of magnitude reduction in contamination rate is great. And this is going to be useful for the LSST surveys because this is probably how we're going to be able to select brown dwarfs by using this machine learning method, which don't work on 2 dimensions, they work on multiple dimensions, and they can be able to select less contaminants than if we just to make it 2D color or index cut. So here's some example of discoveries. Apologize for the XYZ, but we found around 120 M7, M9 objects. So here I'm showing some spectra of those. So for instance, it's an L1 standard fit to one of the L1 discoveries. So each one on the left side, I'm showing like an image, and then on the top of that, I'm showing a 2D image, and then a 1D spectrum with those regions that we used to select them highlighted. And then we're also able to find a T-dwarf. For instance, here I'm showing like a T7 that's fit to a T7 standard. If you look at the distribution of this object in coordinate space, so in this case, I'm showing R versus Z, we can see that they extend up to 2 kiloparsec in height. So again, the idea of this survey was trying to actually detect this object at 2 kpc or at a kpc level. So this is great. We're starting to actually study this object in high in the galactic disk so that we can understand how brown dwarf evolution and the Milky Way structure fit into one picture. So this is great. So what can we do with this sample? So I'm going to talk a little bit about how we can measure galactic structure with this sample. And here by galactic structure, I'm also going to be talking about scale height measurements. So to do that, we use a Monte-Carlo simulation framework. And I'm not going to briefly explain every single one of these inputs or outputs, but the idea is we take multiple inputs for distribution such that the mass function, the edge distribution, binary statistics, and then we evolve that into physical parameters, and we incorporate galactic structure into that model. And then we map that to observables, and we add our selection function into this big source. And then in the end, we predict the number of objects that we should be able to detect as a function of type. And we can also predict the magnitude distribution or the spectral type distribution. So we scale this. So the output of this simulation can be scaled to the local luminosity function. So here I'm showing different predictions based on evolutionary models. So you can see that there are divergences between different evolutionary models, mostly how they parameterize their cloud formation in the atmosphere. And then we can just count how many objects in the end we have. So the idea was to just see how the number counts fit to these expectations. Since brown dwarf cool down with time, we expect that they cool down to low temperatures. So I'm showing again that evolutionary model from Burroughs et al. So on the x-axis, I'm showing logarithmic age, and then on the y-axis, I'm showing temperature. And since brown dwarf cool down with time, we expect this object to pile up at the lower at a lower temperature limit. And then, but there's also a volume effect there. And also, yeah, so since brown dwarf that are colder are fainter. But you can put this into one big, again, simulation and just get the number count as a function of spectral type. So this is what I'm showing here. On the x-axis is a spectral type bin in 5 types because we didn't have enough object as a function of spectral type to actually measure this in more finer bins. On the y-axis, I'm showing the number counts. Each one of these dots is a measurement. And then each one of these open dots is the measurement, but outside our magnitude limit survey. So we carefully compute the magnitude limit of this survey, and then we actually made a cut both in the sample and the simulation. So that's the difference between this open circle versus closed circle. And then each one of these line is a prediction based on different scale height assumptions. So we explore scale heights between 100 and 1,000 parsec. And then again, scale height, if you remember that, is just how fast does the density fall off in exponential terms. So that's what this formula is showing. So the density will go like an exponential in z as a function of scale height. So once we measure scale height in this simulation, we're able to also measure velocity dispersion by transforming that scale height into velocity dispersion. And then using known age velocity dispersion relations. For instance, here I'm showing, that's what the second equation is. And then the idea here is that as objects get older, with time, they interact with structures in the Milky Way, such as spiral arms or molecular clouds, and they get kinematically heated in a disk. And they get, basically, older objects are more kinematically dispersed. So on the x-axis, I'm showing the subtype versus the age of the population. The simulated here means that if you just look at the object at the end of this simulation, this Monte-Carlo simulation, what is the distribution in age? And then inferred here means if you measure the scale height and transform that scale height into age, what's that distribution? And the spread here is mostly from Poisson error bars in the pink distribution. So this is kind of tracking the median age of that population. As with expectation is that our expectation is that L dwarf will be a younger population because L dwarfs are again an evolution of L dwarf evolved towards cooler temperatures. So if you just look at L dwarfs, there should be a younger population, which is what this plot is showing. So if you look at M7 versus M7, M9 versus L0, L4, you find that L0, L4 are a younger population on average. But we're not able to put some constraints on the distribution in age for T dwarfs because again, we have low number counts. Just to summarize this part of the talk, with the HST surveys that we're able to find 164 distant ultracool dwarfs, and we're able to estimate their scale heights and their ages, and we're able to find that these are mostly consistent with what we expect from evolutionary models, but we're constrained by the number counts of T dwarfs. And there's also some systematic uncertainty in the age estimation because of low number count, because of evolutionary models, and then also because of different age velocity dispersion parameterizations. So I'm gonna now jump onto our Kickstarter grant, which is on how we're gonna do the same kind of study with the Rubin Observatory. So to do this, the idea was to predict how many Brandorf we expect to observe with the Rubin Observatory, and also to see how we'll be able to select them outside of larger population. So we're going to use the same Monte-Carlo simulation framework. In this case, I'm showing again that framework where we have a bunch of inputs, we have observables, and then we map into that. We map that into our selection function, and we can get number counts out, or colors, or kinematics, or magnitude distributions. So to do this for LSST, we had to compile spectra and models and photometry for different non-brown dwarfs and subdwarfs. So here I'm just showing a table of those compilations. So we had 7,000 brown dwarfs from the Bessarab 2018 paper where they have photometry and Gaia astrometry. And we had some templates, some optical templates from Caselli 2017. We also had some subdwarf spectra from Zhang 2018 and some other subdwarf spectra from Logier 2018. And we also did a SIMBERT search of non-ultracool dwarfs that are subdwarfs. And then we also had evolutionary models and spectral models from Line 2021. These are low metallicity models, but I also have zero metallicity models. So for instance, here I'm showing some of those models. This is the first spectrum here. is the low Z model of solar metallicity with effective temperature of 1000 Kelvin, and then versus a metal poor model, which is minus 2.5. You can see that if you, so what I'm plotting here are different filter profiles for the LSST. So we're able to convolve the spectra and the models with these filters to actually compute what we expect to see as the magnitude or the colors of these brown dwarfs in the LSST survey. So I'm just going to show some of the expected counts. So for instance, if you look at single exposure, assuming this magnitude limits, for instance, Z of 23, I of 24, R of 24.7, and considering something like 18,000 square degrees. And I'm showing here on the x-axis the spectral type versus the number of objects we expect to see. We expect to see around more than, again, thousands of halo stars, and then tens of thousands of thick disk stars, and millions of thin disk stars. So this is going to be life-changing, at least in this survey, because we're going to start actually understand how brown dwarfs evolution fits into the Milky Way picture. And then I also have here predictions for the 10-year baseline. Here I'm assuming like Z of 26, I of 26, and R of 27. Sorry, I of 26.8, and then R of 27. We expect to see larger numbers of halo stars. And then again, we're still talking about millions of thick disk and thin disk stars. So this is going to be incredible. And we're going to actually start understanding how brown dwarfs evolution fits into the Milky Way picture. And then you can ask yourself, how are you going to select these objects? So the other part of this Kickstarter grant is trying to predict what the colors of this object look like. So some of the predictions here. So here I'm showing R minus Z versus R minus I of different populations. So this is where our limitations for this simulation come into play. What I'm showing here is the DPO data from the LSST DPO release. And I believe they include some population of brown dwarfs, but our goal here was trying to model that and see if we match. And then we go to lower temperatures as well. So here we're showing some of those thin disks, which is supposed to be metal-rich population versus the metal-poor population. We kind of follow the trend, but we have a large scatter in these colors because our magnitude relations have a huge uncertainty. And then we also have the same prediction for R minus Z versus G minus R. Here I'm showing what DPO data looks like versus, again, a typical dwarf versus subdwarf population. They seem to fit into this trend, but we have some, again, a large scatter, and then we also keep exploring even towards low metallicity objects. So in this case, we're only using subdwarf versus dwarfs, but we should also include objects that are extreme subdwarf or USDs. So this is, again, a starting point, but I would again talk about our limitations and what we plan to do in the future. So just to put this in the context with other surveys, here I'm showing the distance for an L0 dwarf versus the area of different surveys. So HST, our HST, and this is again on a logarithmic scale. So our HST survey, we're able to find brown dwarf at 1 kpc, which is great. But we're limited in area. We only had like 0.6 square degrees on the sky. If you look at JWST, it's going to do the same kind of study. So here I'm showing two typical surveys, such as the JWST Jades and the JWST Passages, but there is also JWST Glass. They're going to do the same kind of study as our HST survey. So the idea is they're looking for high-ratio galaxies, but they get contaminated by brown dwarfs. But they'll also be limited in area. If you look at Euclid deep surveys, this is probably going to be 40 degrees square on the sky. So this is large, and it's going to also be deep. So we're going to start seeing L dwarf like 5 kpc. Here I'm showing like the Subaru hyperspectrum surveys. These are large in area. So we're starting talking about 1,000 square degrees or 10,000 square degrees. And also Roman is going to be great for this. And so Rubin sits here around, so here I'm showing the 18,000 square degrees. So that's the Y survey. And this is comparable to Euclid. We're still going to have only going to be sensitive to KPC, like KPC distance, but we're going to have millions of these objects. And this is going to be great. So for instance, JWST surveys are going to be great for doing studies like understanding the halo mass function and how that change over different, if there are any variation in the halo mass function. And then the Rubin and Roman surveys are going to be great for selecting just large numbers of this object that could be followed up by the next generation of fiber fed spectrographs. But also understanding better the kinematics of the Milky Way population. So basically, what happens if you were to look at the tumor diagram of all the brown dwarfs that are in a disk versus thick disk. So we're going to have large numbers, and this is going to be great basically to resolve all this. This is going to be adding a high resolution in phase space. But in terms of just comparison, Euclid is probably going to be like Rubin, and we're going to have almost the same area and the same sensitivities. Just to show some of the future work, in this work, we're limited by our models and templates. We don't have a lot of metal poor objects to actually simulate correctly what they will look like and how to best select them. So to do this, we're going to have to just use models that also take into account non-solar abundances and have a better understanding of halo populations. And then for the selection methods, we will explore machine learning as a possible selection method instead of just making boxes in color space, as it was shown with our HST work and other surveys, is that if you use machine learning methods, you are less prone to contamination. So we're going to try to explore these methods, also adding in purple motion and or reduced purple motion. So with that in mind, I'm going to stop here, and then I can take your question. Thank you.
Excellent, Christian. Thank you very much for that talk. And I know there will be several questions, so please go ahead, everybody, and put your questions in the chat for Christian. And I would like to take the chair's prerogative, if I may, and kickstart the conversation. I'm interested in how this impacts survey strategy, because I don't think brown dwarfs have featured too much in our discussions of the best survey strategy for LSST yet. And you mentioned that you had taken the baseline version 2.0 and looked at the population that you would expect to discover in that 18,000 square degree area. Most of that area is actually outside the galactic plane. So presumably that it impacts quite a lot the population that we would expect to see. It's primarily going to be the halo rather than the thin disk or thick disks. So can you comment a little bit about what your preferred strategy would be to get a better overview of the whole brown dwarf population of the galaxy?
Thank you for the question. If I understand correctly, your first question is, sorry, your first question was whether we can, whether there's been a lot of studies on the best strategy to select the subjects, and then, sorry, I kind of missed your second question.
Really,
Sure.
I'm focused on what is the best way for us to study the brown dwarf population, given that the original LSST survey strategy focused mostly on fields away from the galactic plane, where you're looking at one component of the galactic population, but not the thin disk or the thick disk. Is there anything that we could do to moderate the strategy to give a better comparison between the populations? Yeah,
so there's the paper on the best parallax strategy to get better parallaxes for brown dwarfs, but just in general on how to get to kind of target all these populations. The best strategy will be to look at random pointings, but LSST is limited because they're in the southern hemisphere. And they're and then for this case, I'm not simulating only. In this simulation, I'm only showing I'm showing DP0 data, but I'm simulating just random pointings here that are probably closer to what you expect in a galaxy. But again, these simulations are limited by not having any metallicity dependence, so non-solar dependence in the spectra that we have, non-solar abundance dependence. So I'm not sure if I fully understand the strategy well to be able to comment on the best way to optimize this for brown dwarfs. But looking for random pointings or going to, even if you look at one deep field, of course, it's going to be, you're going to be sensitive to a range of populations if you look further. So, yeah.
That's very interesting. I think in an ideal world, we would survey the whole sky, but based on your selection criteria, we should be able to cover, I think, most of the visible sky down to the kind of limiting magnitudes that you need for this selection process. So in effect, I think you should get the whole galactic population.
You're saying that the LSST will be able to survey almost all of the sky?
I believe so. I think at least it should be able to get down to deep coad images at the right limiting magnitude in these filters. At least I think that's the hope.
Oh, okay. Yeah, that'd be great. Yeah, that'd be great for our galactic archaeology studies.
Absolutely. Well, thank you. And I see we have a question from Marcus. Marcus, do you want to comment out loud?
Yeah, sure. So I was just wondering that your method would be very valuable for excluding or to supporting the Roman microlensing survey, which will also look for free-floating planets or unbound planets. So some of them might be UCDs, and so your approach could really help to distinguish or basically tell that they are not UCDs. Have you considered that?
So if I understand the question is whether LSST will be able to confirm any of the Roman microlensed Ultracool Dwarfs that could also be free-floating planets. Is that the question?
Yeah. So the question really, I was really thinking more about, could you have you considered the possibility that you could help distinguishing between free-floating planets and UCDs?
Yeah, so that's a good question. I'm not sure if we can distinguish between free-floating planets and UCDs just because of just from the colors themselves. Because if I bring back those spectra again, so typical free-floating planets will also look like this spectra of very cold ultracool dwarfs. But if we get additional motion information, and if we understand abundances better that are not just the bulk metallicity, because there's some studies on planet formation that predict different abundance distributions. So maybe we can be able to distinguish from that. And this is hard to do with just colors. That's why the work that we're going to do in the future of trying to incorporate non-solar abundances into our modeling framework could be useful. So we could distinguish between different abundances, different alpha to Fe, which is different C2O ratios. Based on this, presumably in the future, this machine learning framework, if we can do that, maybe we'll be able to distinguish between free-floating planets that Roman can find versus ultracool dwarfs. Is that kind of answering the question a little bit?
Yes, it is, because also we have to assume that the source star that we're using for the lensing is very, very faint, and then only in that case that would work. So yeah, thanks very much. That was very helpful.
Thanks, Marcus. And I see we have another question from Jeff Curlin. Jeff.
Yeah, thanks for a great talk, Christian. I was just wondering if there are, I think when you went through your simulations for Rubin, that you were showing all of the objects that you simulated. If you just select out only the brown dwarfs and leave the M dwarfs out of the sample, do those occupy a sort of a unique position in any color space?
That's a good question. So the question is whether, if you look at brown dwarfs in this color selection that I've made like yesterday, if you look at brown dwarfs only, if you don't include, so this is just to orient you. This is starting around like M5. So I'm simulating mostly things that are, ultracool dwarfs. So we start at M5 and below. Okay. So I think in this, at least in this color RZ minus R minus I think these are the things that are on the further right of the plot. So those are, I think, the color object, but I could also color this by spectral type. This could be much better way of visualizing this. This is also true for this color that so G minus R minus Z. It's mostly things that are again on the right hand, top right. So that's probably where this brown dwarfs will sit. Again, this is starting at M5. So if you mean just L and T dwarfs, yeah, that's the other thing we don't have here is we expect it to have like more. I didn't scale this to the correct number of stars that you expect to see. I was just kind of simulating where they will live in these color plots. So they may just be not a lot of objects in this yellow blob that I'm showing. In reality, when you look at the survey, so this was just not scaling to the correct number of stars that you expect to see in this survey. Just trying to see exactly where they will live. Again, this is work in progress, and we are kind of iterating on it.
Yeah, I guess the thing that was striking to me is that they may not separate themselves very well from the earlier M dwarfs in these color plots, and so I was wondering if there are things we can do to improve that situation.
Yeah, that's a good point. I think they will. So again, just looking at this trend towards rightmost part of the plot, I think maybe you could select those that way. But if you look at like in this case, I minus Z of 1 versus R minus I of 2, it seems like you have just a lot of sources there that are together. This is where we can do multiple combinations of color, reduce purple motion, and use some kind of machine learning method to select them. So that's my next. Once I believe this simulation, I will try to explore multiple ways of selecting objects.
Yeah, thanks. I look forward to seeing that.
Thank you.
And that segues nicely into the next question from Carla Peñas Ramirez. Go ahead, Carla.
Thank you, Christian. I will try my best to speak. Have you explored unsupervised machine learning techniques to separate the populations? Because in your training sets, you have a few late T dwarfs, but a huge population of L dwarfs.
So could you repeat the question again? This is about the HST surveys.
Yeah, and maybe it's also applicable for the separation of the dwarfs in the LSST filters, is to try to explore unsupervised learning instead of supervised learning.
Yeah, that's a good point. So the question, the rationale is that the number of T dwarfs is much lower than L and M. So we should do some kind of unsupervised learning to see what's the best, instead of trying to supervised learning method. Is that a
Yep.
Yeah, so totally, that's something we can do. So my initial predictions here for the 10-year period, at least, there's again the question about like imbalance of basically the ratio of L dwarf to T dwarf is M dwarfs. That's a legitimate concern. So we have much fewer late objects and metal poor objects compared to early objects that are also metal rich, and some that are metal rich. So we expect those numbers to be higher than the opposite. So yeah, I would totally explore supervised learning methods to do that. Unsupervised learning. Do you have an idea of what could work best in this case? A specific method that you were thinking about?
Well, there are plenty to work with, but some multidimensional like HST scan or things like that, I think it will work. If you're interested, you can reach me out.
Yeah,
Thank
totally. Yeah, I will totally talk to you. Yeah. So that would be a great idea to explore, especially in this stage of the simulation. Would be great to explore all kinds of selection methods.
Thank you very much. Are there any other questions? I was interested, Christian, that you had enlisted some pupils and citizen scientists in developing the supervised machine learning technique. Is that something that you would plan to extend to LSST data through the educational program?
Yes. Yeah. So the question is, so for this case, we only use students, no citizen scientists. Sorry if I mischaracterized this. So they've been, this is definitely something we can do, the LSST, just training a lot of people to find all these objects. You talked about a citizen, there's an outreach program that we can take advantage of.
Yes, Rubin has quite a substantial education and citizen science program, and they, at the last project workshop, they expressed an interest in working with scientists such as yourself with projects that citizen scientists can contribute to. So I would recommend that you reach out to the Rubin educational program and explore that option. I'm sure they'd be very glad to hear from you.
Yeah, that would be great. I would totally reach out to them. Thanks for mentioning that.
Absolutely. Well, I think that's about all we have time for today. So, Christian, thank you very much for a really fascinating talk. That was most interesting. And thank you all for attending. I will post the recording of this talk, so feel free to share the link with anyone who may not have been able to join us in person. And I wanted to draw your attention to the fact that we will be having more Kickstarter talks later on this week. So do look out for that announcement. And thank you all very much once again. See you next time.
Thank you.